Alright, we're now going to do the molecular shapes of I and J. Now, both of these happen to be ions. That's only going to affect us on the polarity, so we'll look accordingly. Now, this one's a little odd because some of you are thinking, okay, it's a metal. Can you do that? Yeah, because some metallic bonds actually border on covalent or are covalent. They tend to not be, but there are exceptions to every rule. So tin has 4 valence electrons. Chlorine has 7. There are 3 of them. And what do we do with the -1 charge? We add it in. So that's 21 plus 4, which is 25, plus 1, which is 26 electrons. Alright, so it works identically the same way. Tin will be our central atom. We have chlorine, chlorine, chlorine. So we're going to fill the valence shells of the external atoms, and by external I mean the ones that are not the central. So we're up to 24. We have 2 left over, so we're going to put it on the central atom. Now everybody has an octet, but we're not through with this structure because this is an ion, so we have to designate that there's an extra electron somewhere in there. Remember, it's not until we deal with formal charges, and I will do that on a second or a different video, that we have to designate who's got it. So right here, we're just going to stick with the negative all over the place. Alright, so that brings us to 4 electron regions, 3 bonding, 1 non-bonding, so that means we're a tetrahedral electronically. Now, molecular wise, remember when we do our structures, okay, these are in the plane, this one's going back and this one's coming out. It doesn't matter where we place our lone pair. By convention, I tend to do it at the top just because it's easier for me to see, but you do it the way you want. And remember, the lone pair is going to be pushier, so it's going to want to push down, so it's going to distort the angle to be greater than 109.5 degrees. Now again, we can't see that angle because remember, lone pairs are like glass. They have an effect on shape, structure, etc., but you can't see them. Now that means that it is going to affect these angles down here. And again, because it's a tetrahedral, we're going to start with the 109.5, but because the lone pair is going to be pushing against them, we know it's going to distort them and it's going to go down. If that's the case, then I don't have a pure tetrahedral for my molecular. What I have is a trigonal pyramidal. So basically a pyramid with a triangle base. Okay, so, and I'm gonna not draw this well, but okay, so what you basically have here, whoops, is right here. This is what you're seeing. This is from the central atom here. So this is the trigonal pyramidal structure. Okay, and as I said, drawing is not totally my forte. So here we go. So we're now we've done our bond angles. Up here we did those kind of as we went. Now D is polarity. Wait, polarity. Polarity is a partial positive and negative in a molecular compound. We don't have a molecular compound, so we have to designate that we know this. So it's an ion. So it's ionic, or you can put ion, it doesn't matter. But there is no polarity here because it's not a neutral molecule. But we do have hybridization. So for hybridization, we're back to 3 singles and 1 non-bonding. That, last time I checked, adds to 4 regions that have to be hybridized. If that's the case, then I start with 1 s and 3 p's. So I have 4 sp3 hybrid orbitals. Okay, so we're done with that one. Now This one is a little interesting because we're using one of the noble gases. We said they didn't react, and they don't tend to. However, in a lab, you can force them to react with something that's really, really electronegative, which here is fluorine. All right. So again, we're just going to look at the valence electrons. We're going to have 8 from xenon. And we're going to have 7 from fluorine, which we have 5 of, but we got that little positive charge, so that means we're going to subtract 1. So 7 times 5 is 35, minus 1 is 34, which gives us 42 electrons. And again, remember, sometimes it's the math that gets you. So xenon, of course, will be our central atom. We've got fluorine, fluorine, fluorine. Now, I'm going to go ahead, since I got to get my 5 in here, going to put them kind of like that. And so I've got to, again, complete the octet of all the species attached to the central atom. And notice I'm putting them in pairs. And the neater you keep them, the easier it is for me to grade them. And that's always a good idea. Okay, so now I've got 5 times 8, which is 40 electrons. I got 2 left over. So where do they got to go? They've got to go on the central atom. So I'm going to put them over here so that they're not abutting any other bonds, so they're easier to see. Now, that being the case, if when I count, I've got 1, 2, 3, 4, 5, 6. I've got 6 electron regions around my central atom. So that's going to dictate that my original shape is octahedral. Alright, now octahedral, unlike trigonal bipyramidal, is kind of like a square with up and down. All the angles are 90. Then that's easy to see when you got it all together. Now, if what you're doing here is you're putting the species on, and for simplicity, I'm going to put the lone pair. Now, this structure is easier to see if you're using a model kit, to understand that it doesn't matter where you put it, you're going to get the same thing. So basically, if you have the trigonal, planar, bad drawing again, then you're going to end up with a pyramid again, except this is going to be a square base. So the shape of the molecule is going to be square, pyramidal. Now, angle-wise, yeah, in theory, the lone pair is going to try to push, but you can't push far from 90. So all the angles are going to stay 90 degrees because there's nowhere for them to go. The lone pair is going to try to push, but you can't move if you can't move. Alright, that brings us to the polarity. Now, if we were looking at a neutral molecule, we would look at it and say, oh, wait, it's unsymmetrical, so it would be polar. And that would be true, except it's well, let me go ahead and say that we did the angles up there. So if we're looking at polarity, it's an ion. And usually that's an easy one to miss. So there's your ion. Hybridization, we're going to have 5 singles, bonds, and 1 lone pair. So that's 6 hybrids. In order to get 6 hybrids, we'll start with S, always. We only got 1. How many P's? We get 3. We're up to 4. Then we have to add D's. Wait a minute. Right now we're at 5, so let's move that there. So if we add our exponents, 1 plus 3 plus 2, we now have 6 hybrid orbitals. So this ion is an sp3d2 hybrid.